A star's lifespan is dictated by a continuous release of internal energy. By adding protons or neutrons to atomic nuclei, stars generate the outward thermal pressure necessary to hold back the crushing force of their own gravity. This chart displays the Bethe-von Weizsäcker mass formula, which tracks how nuclear binding energy per nucleon changes as elements grow heavier. At first, fusing lighter elements together increases the binding energy, yielding a net positive release of heat. This progression has a specific mathematical limit. The curve peaks here at iron 56. At this exact point, an atomic mass of roughly 60 with 26 protons, the nucleus reaches its most stable state. Beyond this peak, the thermodynamic math inverts. Fusing iron requires a net input of energy rather than releasing it. When a star begins fusing iron, the core starts absorbing its own thermal energy, effectively cooling itself from the inside. Reaching the iron limit ends the star's ability to support itself. Without outward thermal pressure, the internal engine stalls, leaving the star vulnerable to the unchecked inward pull of gravity. In stars exceeding 8 solar masses, this transition is visible in the internal layering. While the outer silicon shell continues to burn, it constantly deposits heavy iron ash onto an inert central core that can no longer sustain fusion. This iron core is supported only by electron degeneracy pressure, the resistance of electrons being crushed into the same quantum state. However, this pressure has a hard physical ceiling called the Chandrasekhar limit. When the core's mass reaches roughly 1.4 solar masses, this quantum support fails. The inward gravitational pull instantly overcomes the electron degeneracy pressure. The physical structure of the core is no longer capable of resisting its own weight. This triggers a catastrophic freefall. The entire stellar core collapses inward in mere seconds, crushing subatomic particles together as the surrounding space compresses at a fraction of the speed of light. This mass threshold is the tipping point. It transforms a stable stellar engine into a collapsing environment where gravity has complete control over the core's destiny. This technical simulation of a core collapse shows that the inward motion is not uniform. The core separates into distinct regions. The inner core falls as a cohesive unit, while the outer core plummets at supersonic speeds, detaching from the matter above. The collapse stops when matter reaches absolute nuclear density, roughly 10 to the 14th grams per cubic centimeter. The strong nuclear force becomes repulsive, halting the inward motion. This triggers a massive pressure shockwave, sending energy outward through the infalling material. However, as the shockwave moves outward, it encounters the enormous weight of the remaining stellar envelope. It loses momentum, eventually stalling against the flood of infalling matter. The mechanical bounce by itself is insufficient to eject the star's layers. To drive a full supernova explosion, the system requires a much larger energy source to restart the outward motion. This equation calculates the total gravitational potential energy converted into heat during the core's collapse. For a 1.4 solar mass core, it generates a staggering 3 × 10 to the 53rd ergs. Compare that to the actual kinetic energy observed in a Type II supernova's ejected mass, which accounts for only 10 to the 51st ergs. This chart shows the energy discrepancy. The visible explosion is a sliver, the supernova's energy. Because they are nearly massless and interact so weakly with matter, they serve as the primary cooling mechanism, draining the energy away from the core. Under typical conditions, neutrinos pass through matter effortlessly, traveling through entire planets without hitting a single atom. But the proto-neutron star reaches densities of 10 to the 12th grams per cubic centimeter. Here, the neutrinos collide so frequently with the densely packed nucleons that they become physically trapped within the core. They are forced to diffuse outward along a jagged path, losing energy with every collision. A neutrino starting at 300 mega-electronvolts in the center is degraded to about 20 mega-electronvolts by the time it reaches the surface. This diffusion timescale equation allows us to predict the duration of the energy release. Based on the core's radius and density, the escape process takes roughly 10 seconds. The supernova is not an instantaneous flash of energy. It is a grueling 10-second storm of neutrinos diffusing outward, providing the sustained pressure needed to restart the stalled shockwave and blow the star apart. Testing this model requires massive underground detectors like Kamiokande 2 and IMB, which use thousands of tons of water to catch rare neutrino interactions. In 1987, a star collapsed in a nearby galaxy, providing the first opportunity to observe this neutrino storm in real time. This scatter plot shows the raw data captured by terrestrial detectors during the SN 1987A event. Each point represents a single neutrino interaction. The x-axis tracks the time of arrival. The data points form a cluster that spans 10 seconds, matching the theoretical diffusion timescale we calculated for a dense stellar core. The y-axis tracks the energy of those neutrinos. Most arrive at approximately 20 mega-electronvolts, exactly the energy level predicted for neutrinos that have diffused from the core center to its surface. The precise alignment between the nuclear binding energy math, the diffusion equations, and this captured data confirms that our understanding of core collapse is accurate. The spectacular visual explosion of a supernova is the residual 1% byproduct of an invisible 10-second neutrino storm. The brightest light in the universe is merely a leftover of the core's massive energy release.